All right, everybody, welcome back. We've been talking about this idea of fluids, and in the last class we were talking about this idea of fluid flow. And when we're discussing fluid dynamics, the study of fluid flow, it really boils down to two concepts. The first concept is the idea of continuity. Continuity tells you that when you calculate the flow rate in a system, Q, when you calculate the flow rate in a system given by volume over time, in other words, how much volume of fluid moves through the system in a given time, when you calculate this value, it remains constant within that system. Now this is true so long as your fluids are incompressible, meaning that the density does not change, and that we have something we would call laminar flow. It just means that the flow is smooth, there's no turbulence. We're not going to worry about turbulence, so in the case of this class, your fluid flow will always remain constant. So we think of a system, perhaps a system which goes from a thin pipe to a wide pipe, and we flow some fluid down that pipe. That fluid will change in speed depending on the area. This is a consequence of continuity. So we identify 2 points in our system. Perhaps we identify point 1 and point 2. We look at 2 different locations. Point 1, point 2. We look at those 2 different locations. The rate of fluid flow Q must stay constant. And as a result, we found that when you multiply the area of that tube, the cross-sectional area, by the velocity, that is also going to give you flow rate A2V2. Flow rate must be the same in both areas, right? This is something we derived last time. This is a consequence of the incompressibility of fluid and the fact that fluid doesn't just magically appear or disappear from within our system. So continuity is our first step. The second thing we learned about fluids, well, continuity is strictly a kinematic property. A way we can describe fluid flow doesn't talk about the causes of fluid flow. We talk about the causes of fluid flow, the actual dynamics portion of fluids. We are dealing with energy. Because dealing with Newton's laws and fluids is very difficult, we deal with energy. And energy is of the form of Bernoulli's equation. Bernoulli's equation, hope I spelled that right. Bernoulli's equation tells us that when we look at these 2 different points in a pipe, whatever that pipe looks like, or whatever the system looks like, when we look at 2 different points, the pressure added to the kinetic energy, but our kinetic energy looks a little different now because we use density instead of our mass. The densities are standard for fluids. 1/2 density times the velocity at that point squared. That's our kinetic energy term. And then perhaps we have our pipe increasing or decreasing in height. If it increases and decreases in height, then we would also have potential energy. Instead of mass, mgh, we use density, rho, but then g times the height at point 1. So perhaps our pipe doesn't look like this. Perhaps we have a pipe that goes from one height to another. We would have h1, h2, having some delta h between them. Whatever you define your initial height to get your final height, they separate by some delta h. And again, this is just to say at that second point we have a larger amount of potential energy. Okay. Energy is important because energy is conserved. This is the energy available at the first point that must equal the energy available at the second point. So we have pressure 2 plus our kinetic energy, 1/2 rho velocity 2 squared plus rho g h2. And this is conservation of energy. This is Bernoulli's equation. Applying conservation of energy to fluids. This is the dynamics portion of fluid dynamics. We have Bernoulli's equation and continuity combining to tell us everything we need to know about fluids which are incompressible and which flow smoothly. Meaning, again, we're not dealing with turbulence here, just fluid flow, smooth fluid flow. So now we have this foundational understanding of fluid dynamics. We begin to question, why do we study this and what applications does it have? And as it turns out, Bernoulli's equations and fluid dynamics, incredibly powerful tool. Bernoulli's equation and continuity can tell you things like why does an airplane fly? It can tell you things like why during a hurricane does a roof rip off a building. It can also tell you interesting aspects of your own health. And we're going to focus a lot today on sort of biological applications of these two ideas. Well, we're really going to focus on one specific biological application as our sort of access point into problem solving. Now, let's take some careful steps to understand how we can approach problems involving fluids, right? We want a methodical approach here. And when we approach fluid problems, we're going to follow a few steps. First thing we want to do is draw a diagram. Not necessarily a picture, because sometimes the pictures can be quite complex. We're going to draw a diagram, a representation for our fluid flow. It's not going to be exactly lifelike. We're using pipes to represent a great many things. We're going to draw a diagram to represent those different systems. We are going to identify knowns and unknowns. And when it comes to fluids, there are specific values that we are going to be concerned with. Some of the important values that we want to know are pressure. Pressure is going to be important. So what is the pressure? Do we know the pressure at point 1? Do we know the pressure at some second point? Because we are identifying fluid as it flows from one point to another. Do we know pressure P1, P2? And can we identify whether they are gauge pressure or absolute pressure? What is given to us in these values? When we understand the pressures, we can understand what direction fluids flow in. What else do we care about? We care about velocities. Now, you might wonder, why am I spelling all of this out? It's because we use V to represent several different aspects during these problems. Bless you. So when I use V lowercase, meaning without the serifs, that means velocity. And we have velocity perhaps at two different points because the fluid flows at two different points. Now this velocity can't change within a system. We saw that last time. What else do we need to know? We need to know changes in height. And specifically, I'm going to spell out height above some defined origin. I noticed that a couple of us made mistakes on defining an origin for measuring height with respect to. So remember, anytime you have a height h, we are measuring it with respect to some origin. So we take a look, and if we have some pipe system that changes in height, we go from low to high perhaps, we want to define some origin when we look at point 1 and point 2. The best way to get comfortable doing this is to strike a horizontal line wherever you are defining to be 0, and this can be anywhere. You can say your 0 point is right there. If that is your 0 point, then your h1 is equal to 0. What is your height 2? Well, your height 2 is equal to whatever that value is right there. You always have the freedom to choose the height to be 0 at some location of your pleasure. So choose the height above some defined origin. You can even, if you wanted to, make a different choice. Let's say we wanted to choose our height to be that was supposed to be at point 2. Let's say we wanted our height to be represented at that upper point. You are free to make this choice, but it is important to understand that when you do so, height 1 is now going to be below the origin, and below means something specific. Below means negative. So if your height is below your defined origin, you take it to be negative, but it still is valid within all of these equations that we are looking at. So you need to be able to define some height. Since we're going ahead and listing out most of these values, we also want cross-sectional area. Do we know these cross-sectional areas? Why is this important? This is important because of continuity. Continuity says if the area decreases, our fluid speeds up. Cross-sectional area is to say if we take a slice of this pipe, and we measure that area within the pipe. Other important quantities, density. How can you figure out density? Well, it's a material property. So if you need to know what density is, you can, and most likely you're going to be given it in this class, but if you need to know what density is, you can look up what material is running through your system. Is it water? Is it something else? Whatever it is, it has some density associated with it, dependent on what the material present is. And then I think the final thing, flow rate, I think, is the last quantity that is going to be of importance here. Sometimes you'll be given it, sometimes you'll need to calculate it. How do you calculate a flow rate? Well, it's not too hard. Volume over time. How many gallons per minute is flowing through your system? Or perhaps you're given area and velocity, in which case you can calculate your flow rate. And why is that useful? That's useful because no matter at what point we look at in this pipe, the flow rate will have some constant value. These are the main physical quantities that you will care about when you deal with fluid dynamics, fluid flow. After you set up the problem, there becomes a question of which physical concept do you need? Do you need to use continuity? Do you need to use Bernoulli's equation? Do you need to use both? And when you're doing this, you approach a third step. You're deciding the physical concept you are going to apply here. Either continuity that the area and the velocity are, when multiplied together, are equal at any point in this pipe. And this is used mostly when you have a change in area. When you have a change in area, or when you are given flow rates. Because when you are given flow rates, you can use continuity. If you're given Q, you can use continuity to find out the velocity at any given point. So continuity is used primarily when area is changing or when you're given a flow rate. All right, what is the other important physical concept that might be important? Bernoulli. Bernoulli's equation. Bernoulli's equation is important when you're looking at systems that are changing in energy. What does this mean? This means changing in potential energy. The height is raising or lowering. When you have a pressure difference, meaning that you apply some pressure on one side or the other and you get fluid flow, or you have change in kinetic energy. Now, the change in kinetic energy, if the only thing happening is a change in kinetic energy, you can typically use continuity. But Spell correctly, energy. Bernoulli's equation used primarily when you have some changing energy. All right. So what are you going to do? You're going to solve using one of these physical systems, but before you do that, you need to be absolutely explicitly clear about your labeling. You need to be careful about your labeling and deciding what your point 1 and your point 2 are. What locations are you looking at, and what quantities are related to those physical locations. I saw on tests that it was quite easy to make the mistake of saying a height is associated with initial when actually it was associated with a final location. It's easy to make those mistakes, so be absolutely explicitly clear about what you are defining as your first and second position in your pipe. Once you have those chosen, it's just a matter of solving the problem, completing the algebra. The physics leads up to this step 4. Step 5 and so on is just going to be solving the problem and checking your answer. But these are a great place to begin solving any sort of a fluid dynamic problem. One thing I will recommend is that you solve things algebraically before you plug in numbers. Many times in these fluid problems, you get quantities that cancel out, and those canceling out quantities can be quite useful. In this case, if you look, nearly every term has density associated with it. What does that mean? That means that if pressure is constant on either side of the pipe, well, density cancels out. You don't actually have to plug it in. So you can get cancellations that make problems a little bit easier if you do the algebra first, but that's just a recommendation, that you do the algebra before plugging numbers. Are there any questions about this? Do we feel all right? So let's put this into practice. All right, we're going to start with relatively easy problem. Let me make sure I get the numbers right to what We're going to look at water flowing in a horizontal pipe. It is going to go from an area with a wider opening to an area with a smaller opening. So we have area 1 at 0.05, and I'll put an extra 0 on here just for significant figure purposes. And area 2, a second section in the pipe, has an area 0.020 meters squared. If the velocity in section 1 is given as 1.5, is that what I want to use? Yeah, we'll use 1.5. What is the velocity in area 2? Now we're starting off easy, and I'm putting a lot of numbers into the problem just for shorthand of writing it. But we have this question, we have a pipe that is narrowing from a large area to a smaller area, and it has some velocity in the larger area of 1.5 meters per second. Now we're going to make a hypothesis based on what we saw last time. Do we expect in the second section for the velocity to be larger or smaller than in the first section. Raise your hand if you think that the water is going to slow down in the second section. Raise your hand if you think it's going to speed up. Wonderful. We've got a lot of intuition here. So let's see if this behaves. We're going to go through our steps, right? We're going to go through our steps by first drawing out a picture. Drawing out a picture is supremely helpful. We have a pipe going from some larger to some smaller area. The picture is as easy as that, right? We can start to identify what known values we have. And we can even incorporate them into our picture, right? We identify that we know the area of either side. We also know the speed going through the larger side, so we'll denote the speed of our fluid. Going through. So we've identified our knowns, we've drawn a picture. We now move on to the question of which physical concept do we use. Bernoulli's equation we deal with when we have some changing energy. Here, we're not saying anything about pressure. We can assume that the pressure is equal on all. We can assume that the pressure is going to be not heavily involved in the mathematics. We look at potential energy. We are not raising or lowering in height, so there is no change in potential energy. So Bernoulli's equation probably out. And realizing I've got the E and change. So what do we use? We use continuity. Continuity used when we have a pipe that is changing in area. That is exactly what we have here. So let's go ahead, let's use continuity. Area 1 times velocity 1 equals area 2 times velocity 2. Meaning velocity 2 is given by area 1 over area 2 times velocity 1. Plug that into your calculator. When you plug it in, you should get 3 1/4, or 3 3/4, 3.75 meters per second. Not so bad, right? Not so bad. So we move on to something a little more difficult. An artery has a circular radius of about 3 millimeters. But commonly in arteries, plaque might be reducing the area, right? Plaque might be causing a narrowing of the radius, and we'll say if plaque blocks the artery, to have only a 1.5 millimeter radius. If plaque blocks the artery to only have 1.5 millimeter radius, what is the speed of blood through blockage. Supposed to write this earlier in the problem, and I forgot, so I'll tack it on at the end. Normal blood speed is about 0.4 meters per second. In the artery. So this is true for an artery that is about 3 millimeters in diameter, and if you have a blood pressure of about 100 millimeters of mercury, if you ever go and get your blood pressure tested, this would be about blood pressure of 100 millimeters per mercury. So this is the problem. The question is, what is the speed moving through the blockage? We take this problem, we analyze it by first drawing a picture. What are we going to do? We're going to look at the artery. Here's our artery with a 3 millimeter radius. And what's going to happen is it's going to go through a clog from some plaque. And the plaque reduces the area to have a radius of about 1.5 millimeters. I want to know how quickly does the blood move through the blockage, given that it has some velocity equal to, 0.4 meters per second. All right, I'm going to leave the rest of solving this problem. I've drawn the picture, I've labeled the knowns. I'm going to leave the rest of the problem up to you guys to solve. And then we'll come back together as a class. So find the velocity through the blockage. Time for someone to wake up. we've learned really closely we're going to be on like that's going to be related things. We're going to talk about the movies in the next part. Right now, I'm just dealing with continuity, and continuity is never going to area. To do the algebra first. Yeah, so when you do the algebra first, and I'll talk about it in a second, it's just rearranging the equation before you plug things in. So instead of like having numbers everywhere, you find a variable first and then plug numbers. All right. So we take a look at this problem. It's another problem that involves continuity. With continuity, we say that the flow rate is going to be equal in either section. That is because every drop of blood that flows through the wider region must also flow through the thinner region. It must do so in the same amount of time. So continuity tells us the flow rate must be the same, meaning area 1 times velocity 1 is equal to area 2 velocity 2, where we need to have a good definition of what we are considering point 1 and point 2. At no point did I say the clogged artery is point 1 and the open part is point 2, or vice versa. You have to make that decision. You can make any decision you'd like. For me, I am going to take the perhaps obvious routes. Say my defined position point 1 is going to be the open artery. My defined position 2 is going to be where the clog is present. When we do this, we have now our area 1 being related to the 3 millimeter radius and the velocity 1 related to the 0.4 meters per second. So now we have all of the values we need. We solve algebraically for velocity 2. And this is the exact same equation we've had before. In the prior problem, I gave you the area. This time I gave you radius. You have to calculate out what the area is. So, calculating out the area, we have pi times the radius in the thinner region, I'm going to call that R1 squared, divided by pi times R2 squared times V1. Now, why did I say solve it algebraically instead of plugging in numbers? You could have calculated out what the area is earlier, but conveniently enough, pi cancels out. You don't need to plug in your 3.14 to find the area. I don't actually care what the area is, right? Cancels out, the pi cancels out. What are you left with? R1 squared over R2 squared. Now, another convenient fact. Because I waited to this point to plug in numbers, I can look at this and I can say, well, I'm doing radius divided by radius, or radius squared divided by radius squared. What does that mean? That means I think about the units. The units on the top and the units on the bottom are going to cancel out. This is a ratio. So I don't even have to do a unit conversion here. By keeping it in this form, I can look at these two values. I could say the units are going to cancel out, so it doesn't matter which units I use. If I use millimeters, if I convert it to meters, get the same answer. So I'm going to keep it in millimeters. 3 millimeters squared divided by 1.5 millimeters squared. And you multiply that by the velocity. What did I give you? 0.4 meters per second. So why do I say it's wise to wait to plug in numbers? It's wise to wait because when you get to that final expression, you can save yourself some time to plugging in of pi's into doing some unit conversions. You could do the unit conversions, you could calculate out what the areas actually are, or you can just go through the algebra. In any case, we solve it out and you should find the speed to be, I don't think I have it written out. So what do you find the speed to be? 1.6 meters per second. And in fact, I should have guessed this. If you, because of this squared, if you half the radius, you multiply the velocity by the inverse of a half squared, which would be 4. 4 times 0.4 is 1.6. So we have our velocity in the inner region. The blockage speeds up. The blockage speeds up our blood. Now, taking a step back, let's think about Bernoulli's equation. Because we can look at Bernoulli's equation as it applies to Bernoulli's equation applies to all fluid flow. It's not always useful in problem solving, but it always does apply. And when we take a look at this, we can write pressure 1 plus kinetic energy 1 is equal to pressure 2 plus kinetic energy 2 for this problem, because we are neglecting any sort of a change in height here. And when we take a look at this, I can ask the question, what's larger, kinetic energy 1 or kinetic energy 2? What is the larger value? Kinetic energy 1 or kinetic energy 2? Well, what's larger, the speed in 1 or the speed in 2? Speed in 2. So what's larger, the kinetic energy in region 1 or the kinetic energy in region 2? Region 2. So that means that this is a large value, and this kinetic energy is a small value, a little small in comparison. Take a look at this. These two sides must be equal to each other. Energy says that must be true. So what does that mean? That means pressure 1 is going to be large, pressure 2 is going to be small. We get a drop in pressure at the blockage. We get a drop in pressure at the blockage. And that might not make sense right now because we think about clogged arteries. We think, okay, well, that increases pressure, right? It increases your heart pressure. But that's not quite the physics that's going on here. The physics says we have a drop in pressure. I'll explain what that means a little bit later on. But just a quick analysis of Bernoulli's equation without plugging in numbers. Are there any questions? So we move on to a question involving now Bernoulli's equation. On the board, I wrote the problem. It starts off similar to our earlier problem. Water flows through a horizontal pipe. It does so from pressure on one end that is 150,000 Pascal. Pascals is a very small unit of pressure. 150,000 is like 1.5 atmospheres of pressure, so nothing too crazy high. In the end with 150,000 Pascal, the water is at 2 meters per second. At the other end of the pipe, we see an increase in speed to 4 meters per second. The question is, what is the pressure on the other side? We start off by drawing a picture. What should this picture look like, though? What should this picture look like? Well, perhaps we have a region 1 and a region 2. So I'll start off by saying, here's region 1, here's region 2. But I know that this isn't quite the right picture. How do I know that? I know that because our water is speeding up. If our water speeds up, what do I know about the area? It changes. In fact, it should decrease. So perhaps a better picture would be to make sure we represent that decrease in size. Now, do I know anything about the areas? No. I don't know what the areas are. I don't care what the areas are. But I know there must be a change in the area. All right. We go through and we look at this and we say, well, what's going on here? We have a change in speed, a change in kinetic energy, and some pressure. Remember, pressure is related to work. We showed that last time. So we have work causing a change in kinetic energy. This is a conservation of energy problem. This is a Bernoulli's equation problem. We list out our known values, and I'm going to go ahead and do that on our drawing, but you can make a table if you'd like, where we have velocity in region 1 of 2 meters per second, and velocity in region 2, 4 meters per second. What else do we know? We know that we are creating a high pressure region on the side that has 2 meters per second. I could have flipped this. I could have made the water flow in another direction on my picture. I didn't. So this forces me to understand where the pressure is at the 150,000 Pascal, and that is going to be on the right-hand side. So I say on the right-hand side there's some pressure being exerted, P1 of 150,000 pascals. I'm going to write kilopascal instead of 150,000, but just know kilo stands for 1,000. So we have 150,000 pascal. So what's going to be true? On the right-hand side, we have a change in pressure. We have a change in pressure. This change in pressure is causing the water to speed up. This is the work that is being done. So we apply Bernoulli's equation. And right off the bat, we can do some simplification here. We can do some simplification because our pipe is horizontal. Since it's horizontal, what is our change in height? Wait, what's up?
Not looking at changing height for this one.
Yeah, you're not looking at change in height. Change in height is going to be 0. A moment ago I said we define our origin, right? We define our origin. I'm going to go ahead and define my origin to be at that level that I struck the orange line. When I do that, height 1 is 0, height 2 is 0 because they're both at the origin. So that means the potential energy term goes away. We don't care about it. We're left with pressure 1 plus the kinetic energy term, 1/2 the density times the velocity at point 1 squared. And that must equal the pressure at point 2 plus 1/2 the density times velocity 2 squared. We have Bernoulli's equation. But I know there's a problem here. I don't know one of those terms. Well, technically I don't know 2, right? I don't know pressure 2, the thing I'm looking for. But I also don't know density. I don't know density. How can I figure out what density is? Okay. Think I was hearing it?
The density of water.
Yeah, I know the material. If I know the material, I know what the density is. And water has a very specific density. Going back to the French Revolution, water was defined to have a specific density of 1 gram per centimeter cubed. Exactly 1 gram per centimeter cubed. This is the density of water defined for us. We can rewrite this if we wanted to in our SI units, 1,000 kilograms per meter cubed. Both are the same number, just different units. So now I know the pressure, I know the density, I know the velocities. I can find that final pressure. Change the camera real quick. Email me to the other board. When we take this equation, we can rewrite it. Of course, we can rewrite it as being pressure 2 is equal to pressure 1 plus 1/2 the density times the velocity 1 squared, subtracting off the final kinetic energy 1/2 rho v2 squared. I think I did my algebra right there. Back over to the other side. Now, of course, at this point, you can plug in numbers. I'm not going to do so yet, though. I'm not going to do so because I'm going to further simplify. I'm going to further simplify because those second 2 pieces here have the same 1/2 times density involved in them. So we can rewrite this pressure 2 is equal to pressure 1 plus 1/2 rho times the quantity v1 squared minus v2 squared. Now we have to be absolutely careful. We have to be absolutely careful here because this does not equal pressure 1 times 1/2 the density times v1 minus v2 quantity squared. That does not equal that. You cannot take the squared out, you cannot distribute the squared out. Another mistake I saw in a couple of tests. So we're at this point, this is as far as we can simplify it. We plug in some numbers, and you should find pressure 2 to be 144,000 pascals, 144 kilopascals. We have a drop in pressure. We have a drop in pressure causing our fluid to speed up. The drop in pressure is associated with the change in energy. We drop our pressure in order to get the kinetic energy up. We have a drop in pressure. Does that sound okay? Thoughts, comments, concerns? We feel good about this? An artery has a circular radius of 3 meters, 3 millimeters. Okay. I'll give you the unit conversion here in a second, but typically when we deal with blood pressure, it's measured in a unit that isn't Pascal, it's measured in the units of millimeters mercury. This goes back to how we initially defined this idea of measuring pressure. We did so with mercury-filled objects, and we saw the height of the mercury object change by some millimeters depending on change in pressure. I put up a video about that a while ago, but this is typically how we measure blood pressure. Now, 100 millimeters of mercury converts with the unit conversion. 1 millimeter mercury is equal to, I want to get this right, 133.32 Pascal. 133.32 Pascal. All right. So we have blood traveling through a circular artery, and there's a location where the blood pressure is 100 millimeters of mercury. We're going to say that the artery decreases by some size, and at a plaque blockage, the velocity increases from 0.4 meters per second to 1.2 meters per second. I'll give you all the information. We need pressure 1. Okay. Density of blood, slightly larger than water. 1040, 1060. 1060 kilogram per meter cubed. My question becomes, what is the pressure inside of the artery? What is the pressure inside of the artery? Or you know, a better question. What is the change in pressure, delta P, between P1 and P2? All right, so now we have a problem that involves looking at exactly what that change in pressure is, going back to what I was discussing earlier, as far as Bernoulli's equation applied to the earlier version of this problem. Are there any questions before we get started on this problem? We feel okay about it? Okay, I'm going to let you guys go ahead, get started. Let's solve that problem, and while you do so, I'm going to write up one more problem for us. Raise your hand if you need more time. All right. You guys have it.
Like the standard units for practice. How is it like the could you use KPO2?
Kilopascal.
Oh, like the 100 times 7.
It just uses the acid weight test. We've done about AC units,
Yeah, because I like set it up so the pressure
SI unit
was
system, the AC unit.
1060 over 2.
But that's not the only unit.
So that's our density, right?
It's
1060,
commonly
we
like
just leave it.
you will see millimeters mercury.
Oh, we don't
H
change
is
it
the
to
standard
grams,
unit.
but I remember we had, I guess water wasn't great enough, but grams centimeter.
So, you know,
But it doesn't
what
matter
is,
what it's-
what is the base unit?
Because sometimes we get to like, because we're working.
What's that?
Sometimes we get to versions like yeah, so we can use the.
And in this class, right, you can talk about the base unit of the computer, could be CSI. That's easy.
Yeah, that's what I'm getting. The units are weird.
So like the units for this problem.
For the first one, okay.
Yeah, you want it.
The grams with the water. Or did we just keep that for the pressure?
All right. Change in pressure, what do we have? Raise your hand if you have an answer. I saw your answer already. Let's go right.
Negative 678.4.
Negative 678.4 pascals. All right. So we have this negative 678.4 pascals. Anybody calculate this in millimeters mercury? Okay, well, go ahead. Divided by 133.32. Tell me how many millimeters of mercury this changes.
Negative 5.08.
Negative 5.166. Again, we typically use millimeters of mercury in medicine for our pressures, so why not stick with it for this biological application of pressure changes? But these do mean the same change in pressure physically, just different units. And when we look at this, we say negative 5.1 millimeters of mercury. What does that mean exactly? Well, what that means is that we've used up some of the energy that came from the heart to get the blood to flow through this narrowing. We can come up with this sort of very simplified idea of how the heart works. And how the heart generally works, my anatomically correct heart. Your heart feeds a bunch of arteries, veins, and all of that stuff. So we have essentially big tubes coming off of the heart to carry the blood. What happens? Well, as the tubes get further away from the heart, those tubes thin. They break apart, get even thinner. They break apart, get even thinner, until you get some very, very thin tubes in your body, right? Now, every time we have a thinning of the tubes, every time there's going to be some change in pressure associated with that. And if you add together all of the change in pressures, all of these small 5 millimeters of mercury, 2 millimeters of mercury, all these small changes, when you add them all together, that is the total amount of pressure the heart needs to provide. So bigger change due to a blockage means that there is more pressure the heart needs to produce in order to pump blood through that region. And that's why if you have blockages getting severe enough, this change in pressure becomes large enough that the heart can no longer supply the pressure to it. That's when you start to have very severe health side effects. But this is essentially the idea of how the body produces your change in pressures. Now, this is very simplified. Why is this very simplified? This is simplified because we are assuming a few things in these fluid flow problems. We are assuming that your fluid is incompressible. Well, that's true with blood. You're assuming that your fluid flows smoothly. With blood, it kind of does, but there's a third assumption you're making. That third assumption is that your fluid does not have viscosity. When you get to very thin arteries and veins, very thin artery and veins, viscosity plays a huge role. In the larger regions, not so much, but when it thins down, it does. And you'd have to go into a little bit more advanced physics work to understand how viscosity plays an effect on that. This is where we will stop with our analysis of fluids. I have one more question for you guys, but before we do that, I'm going to ask you, how are we feeling? Are there any questions out there that you guys have? All right, final question I am going to pose to you. About 6 minutes left. So final question, section of an artery is partially blocked by plaque. Upstream of the blockage, the artery has a radius of 2.5 millimeters, and the blockage narrows it down to 1 millimeter. The viscosity upstream of the blockage is 0.3 meters per second, and the pressure upstream of the blockage is 100 millimeters of mercury. What I want to know is, what is the change in pressure between the healthy and blocked artery? What is this delta P? Now, what does this problem do? It actually combines the two earlier problems that I gave you. Because in this problem, you do not have enough information to solve Bernoulli's equation right out. Instead, what you have to do is first apply continuity to figure out the velocity and the blockage, just like we did in the first problem. And then once you have that velocity, you can find the pressure, just like we have in this second problem. So this is the problem I will leave you with. You guys can stay and solve it and work on it. I have the answer, and in 6-ish minutes, I'll write the answer up on the board so you can double check. And then that'll be the end of today. During the last 6 minutes, if you did not pick up your test on Monday, be sure to come up here so I can give you your test. As a reminder, next week is our last week of lecture. We will be covering oscillations, possibly getting into waves, although I kind of doubt that we'll get into waves. We'll cover oscillations, and we will then have the exam on the 8th of December. All right. So let's go ahead, let's solve this last problem and come up if you need your exam.